All right, today we are going to talk about the romer model with capital stock. So we are going to combine the solo model with capital stock and romer model with ideas. The combined model is set up by adding capital to the production function of the romer model. It sounds a little complicated, but it's not necessarily that. It's simple. So the model have just one more unknown capital stock on top of the romer model. And then there is only one additional equation on top of the standard romer model. That is the capital accumulation equation from the solo model. So we know that the changes of capital stock toward time t plus 1 is investment deducted by the depreciation, right? So we just add that. Also, we have one more component in the production function of manufacturing sector or food production function. So we put the capital stock like utensils for food production, and the exponent of capital stock would be 1/3 as it was in the solo model, and the exponent for the labor in the manufacturing sector in particular. So it has this Y subscript, the workers in the manufacturing sector. But anyway, the exponent of that would be 2/3. Okay. Now this new model will explain the long-run growth of an economy through a balanced growth path with a constant rate of output growth. So we have talked about this in the romer model. So if we put time on the horizontal axis and log of y, the output on the vertical axis, then we have a linear line to represent the log of output and over time, and the slope of this line is given by G, which was new notation for the growth rate of ideas. That was Z, the efficiency of production of ideas, and little l, the share of researchers in the population, and capital L, that was whole population. Anyway, that was from the romer model, standard romer model, and we will see whether this holds for this new combined model of solo plus romer. New thing of this new model, or interesting thing of this new model, would be there will be transition dynamics. So if you remind the solo model, we talked about output, steady state output, and the steady state output changes if steady state output changes, like from Y star to Y double star, then it shows some transition dynamics between these two levels. So if it's far away from the new steady state, then it changes faster. And then, let me erase this thing. And then as it gets closer, faster. As it gets closer, the speed gets slower. So this is fast or steeper slope, and then the slope becomes flatter and the speed gets slower. So this was transition dynamics, an example of transition dynamics of Solow model. And this kind of transition dynamics will be observed in this new model as well, because it is combination of Solow and romer. So if there is a change in parameters, then the economy will show smooth phase in and phase out between two different balanced growth paths. So here is an example of transition dynamics in this new model. So suppose there is an increase in the saving rate, then usually in the Solow model, because saving rate increase, the new steady state capital stock level increase, then output will show like this is the previous steady state, and Y double star means new steady state, and it grow fast, and then as the economy gets closer to the new steady state, the growth rate gets slower, right? We just tilt this kind of transition dynamics a little bit. So rotate this one to counterclockwise, then you have this new transition dynamics of this new combined model. So the the growth rate of this new model is constant and positive. This holds for new balanced growth path as well. So eventually the economy will achieve a certain growth rate, which is the same to the previous growth rate. The slope will be eventually the same. However, when the economy is far away from the new balanced growth path, this one, the upper one, then it grows faster. And as economy reaches to the new balanced growth path, the growth rate becomes slower and eventually it achieves the previous constant growth rate. Okay, so this is the transition dynamics in this new combined model. So I explained that the new model will explain the long-run growth through a balanced growth path with constant rate. The slope is constant, but if there is a change in parameter values, then there will be some transition dynamics. So there will be some phase in and phase out period between two balanced growth paths. All right. When the economy is on a balanced growth path, then the aggregate output and aggregate capital goods grow at the same constant rate, and the stock of ideas grows at a constant rate, which is different from the growth rate of output and capital goods. So let's take a look at the growth rate of stock of ideas. Actually, we already know this. So the stock of ideas grows at this speed, and that is from the definition of innovation equation. We have the efficiency of producing ideas, and then we all stand on the shoulders of giants, the current level of ideas. And then we need researchers. And as many as we have, we can produce a variety of ideas. So we put number of researchers there and divide it by the current level of ideas. Then this cancels out and we have z times little l times capital L. So little l times capital L was the allocation of researchers over time, which was assumed as constant. All right, and then we actually defined and introduced new notation G so that we can present this multiplication of three parameters using just one parameter, G. So that was all the same to the standard romer model. Now let's take a look at the growth rate of aggregate output, capital Y, and aggregate capital goods, capital K or big K. And they will grow at the same growth rate. Why is that? So let's take a look. The growth rate of big K capital goods would be, let me use black one, changes in big K toward time t plus 1 over the current level of capital stock is, if we just use the capital accumulation equation in the numerator, then that is saving rate times output, today's output, minus depreciation. Depreciation rate times current capital stock. And it should be divided by the current level of capital stock. Now we have saving rate times output of today over capital stock of today minus depreciation rate. And on the balanced growth path, this should be constant. So this should be some number, right, like 0.03 or 0.05, something like that. So constant. What does that mean? This ratio, y sub t over kt, should be constant. Okay? That means the growth rate of growth rate of output and growth rate of capital stock should be the same. If you want me to prove it, just ask me on Wednesday next week, then I can prove it. But anyway, this should be constant, so that's why they have the same growth rate. Then we are going to use this characteristic for growth accounting. Growth accounting means that we are going to decompose the contributions of capital goods versus ideas toward GDP. So production function was given by this Cobb-Douglas function. Total output or aggregate output is based on the stock of ideas today and capital goods level to the 1/3 and the labor or workers in the manufacturing sector to the power 2/3. Now take log for both sides, then multiplication becomes addition or addition. So we have these three terms on the right-hand side. And what I'm going to derive from here is that growth rate of output at time t equals growth rate of ideas at time t plus 1/3 times growth rate of capital stock plus 2/3 times growth rate of labor force or workers in the manufacturing sector. Okay, how can I do that? Actually, and then I will actually replace this one to growth rate of output using the fact that growth rate of output is equal to the growth rate of capital goods. Now, how can I derive this one? I will use the first derivative of log. So this is a reminder of calculus. You don't have to know about each step of this derivation, but you need to, you might want to remember the growth rate is derived from the first derivative of logs, just the fact. Okay, let's derive from log to the growth rate, or let's derive the growth rate out of log. So the first derivative of log is actually 1 over the original variable x. And then if we use that, then we can derive the first order condition of a function f of x. So log of f of x is given, then the first derivative of log of fx with respect to x would be 1 over fx times just the first derivative of the function. So f prime of x. Then we can apply that idea like this. So output is actually a function of time. Then apply this formula. So first we put 1 over output, and then we put first derivative of output with respect to time. And then actually this means that if there is a change of time, then the output will change as well. So the infinitesimal change of output would be the meaning of first order derivation. So we put delta of yt, or changes of output, instead of y prime of t. And that means delta y of t over yt, and that is the growth rate of y. So u minus previous over previous. That is the growth rate. Hence, we have the growth rate out of the log function. Okay, so this is calculus. You don't have to remember whole thing, but let's apply this, what let's apply what we just learned. So if we take time derivative with respect to log, then we will get the growth rate. So let's just draw these symbols. Just follow me. It's not complicated. It's like drawing. So we put this operator for each symbol or each log variable. So we put the same operator to log of a sub t and the same operator to 1/3 times log of kt. Again, the same operator to 2/3 of log L sub yt. Then this is the growth rate. So instead of this complicated symbol, I will just put it as growth rate of y at time t. Then this is growth rate of ideas at time t. And this means put the constant 1/3 out of this operator. Then we have 1/3 times growth rate of capital at time t. And then again, put the constant out of this whole operator. So 2/3 times growth rate of L. So workers in the manufacturing sector. So we have this growth rate accounting or decomposition of growth rate of output. Again, growth rate of capital stock is known to be the same to the growth rate of output. Then plug in that, so we have 2/3 of growth rate of output equals growth rate of ideas plus 2/3 times growth rate of workers in the manufacturing sector. But actually this is 0. Why? Because the population does not change and the allocation of workers in the manufacturing sector and R&D sector are fixed. So there is no change at all over time in the allocation or number of workers in the manufacturing sector. So the growth rate is 0 or rate of change is 0. So we can ignore whole thing. Then that means we have this relationship. And we already calculated this one. We already calculated this growth rate of ideas. Where? Well, that was actually we defined as just G without any subscript. G was Z, the efficiency of creating ideas, and the little l, the allocation or share of researchers among population, and the whole population, L. And that was derived from the changes or innovation in ideas over the current level of ideas. All right, so G, the growth rate of ideas was Z times L, little l times big L, and output growth rate, which is constant on the balanced growth path, is 3 times of a half or 1.5 of the growth rate of ideas, this one. Okay, so that was the growth accounting in the Solow plus romer model. Thank you for watching. This was not easy, so please review these slides and go through the derivation one more time, please. We are going to review this growth accounting when we resume the class meeting on Wednesday. Okay? Thank you. Good luck. Have a wonderful fall break. Bye.